Okay, YouTube, in our last video we looked at summation notation, which was really just a nifty way to write the sum of a bunch of terms of a sequence. In this video we're going to define what we mean by a series. So we would say that a sequence, okay, remember that a sequence is a list of numbers in order, such that there's like a first term, a second term, so on and so forth. We say a series, though. What is a series? Okay, we say that considering the infinite sequence a1, a2, a3, all the way out to the nth term here, if that were to go on forever, we could probably a little ellipsis here. We say that the sum of the first however many terms, we refer to that as n terms of the sequence, is called a finite series, or the nth partial sum of the sequence. So we're going to start with this here. We call this a finite series when we add up the first n terms of a sequence. So a series is the sum of the first n terms of a sequence. So there is a difference between a sequence and a series. The sequence is the list of numbers. The series is what we get when we sum up the first however many of those terms of the sequence. So we say that we refer to this as a finite series if there is a last term here, and an infinite series down here if there is no stopping point on your sum of your series. Another part that I want to point out here is that we refer to the finite sum as the nth partial sum, and the root here is part. In other words, you're finding the sum of only a finite set of terms. If we were to look down here, we say the sum of all of the terms of the infinite sequence is called an infinite series. Of course, we would refer to this as an infinite series as opposed to a finite series, because we are summing up the terms of the sequence, but all infinitely many of them. And it's denoted by this here. We'll talk about how they're denoted. But what I want you to notice here is that down here I did not write nth partial sum. So we only say a partial sum, and we refer to really the sum of the first n terms there as a partial sum up here. But because the reason why is down here, there isn't a stopping point. We're going to add them all together. So we just call that the sum. So looking at these two denotations, we can see that in this first one here, if we add up the first, and it's clearly first n terms of this sequence, then we have what is referred to as a series. It is a finite series. And what this says over here is, let's add up from the first term all the way out to the nth term, all the terms of this rule right here. The same thing is written down here, but when we add up all infinitely many of these, never ending, we refer to this as an infinite series. And we just say that infinite series. We say that it stops never. It never stops of all the terms of this rule right here. So let's go ahead and take a look at both a finite and infinite series. So we say for the series, sigma is starting at 1 and going to infinity. So we have an infinite series written right here. But we have 3 over 10i is our rule, 10 to the I. So we're going to find the third partial sum. So the first thing is this. When we write the third partial sum, we really mean this, the sum of the first 3 terms of the sequence. So the third partial sum really just means find the first 3 terms and add them up. So what we end up with here is this situation. Here's our rule right here. We're going to rewrite our rule a little bit. We say I is equal to 1. And up here, instead of ending in infinity, we're just going to stop at 3. We're going to stop at the third term. So our rule is still 3 over 10 to the i'th power. So we're just going to write out our sum here. Our first term would be what we get when we plug in 1 for I here. So our first term, we'll plug in 1 there. Plus now 3 over 10 to the second, plus 3 over 10 to the third. This would be our third partial sum right here. So I'm actually going to take the time to write this as decimals. This would be 0.3, 3 tenths, plus 3 hundredths. 3 hundredths is actually this right here, plus 3 thousandths when you simplify this here. 10 to the third is 1,000. We get 0.003. So when I add all 3 of these up, I get 0.333. So the sum here, the third partial sum, is equal to exactly 333 thousandths here. When we talk about the sum, what we really mean is the sum of all infinitely many terms. Infinitely terms. So when we find the sum of all of these terms together, The interesting thing is I have no rule to share with you at this point on how to do this other than let's look for a pattern here. What I noticed up here was I got 3/10ths and 300ths and 3,000ths, and the next one will be 3/10,000ths. If this pattern were to continue, essentially 0.3 plus 0.03 plus 0.003 plus ... and this keeps going, you could see how this would approach 0.333 repeating indefinitely. So what I'm going to write is the sum of all infinitely many terms of this sequence actually adds up to be a thing that's not infinity. It adds up to be a third. Cheers.